For the most part in this class, we're going to be measuring things with standard units. By that I mean we're going to be measuring mass in kilograms. We're going to be measuring time in seconds, time in seconds, and we're going to be measuring distance in meters. These are the standard units, or what sometimes is called SI units. I know a lot of times we think of grams being the fundamental unit. In this case, we're going to use kilograms. Now, it would be pretty limited if all we could do is measure mass, time, and distance. So we want to measure more physical quantities other than just these three things. And to do that, we can actually combine these different units to come up with units for other physical quantities. Let me give you an example. Here's you. You're running some distance, and you do that in some time. Let's suppose you run a distance of 100 meters in 10 seconds. Make this a little bit neater. So you're running 100 meters in 10 seconds, and you want to figure out how fast you're going. How fast you're going is a speed or velocity. Write that down there, we'll call that your velocity. Your velocity has units of distance over time. That's just going to be delta x over delta t. I'm going to combine the delta x and the delta t. So that'll give me 100 meters over 10 seconds, which will give me a speed of about 10 meters per second. So just like you would measure your car's speed or velocity in miles per hour, miles is a distance, hours is a time, we're going to measure velocity in meters per second. Another thing we want to be able to do is convert units. So suppose I want to take 10 meters per second, but I actually want to measure that in centimeters per hour. How do I do that? Well, to do that, we're going to make use of the fact that we know how many centimeters are in a meter, we know how many seconds are in an hour. So I know that 100 centimeters is equivalent to 1 meter. That's a fact, it's a definition. I can also figure out how many seconds there are in an hour. So I know there's 60 seconds in 1 minute, and 60 minutes in 1 hour. I'm going to use these facts to do a conversion here. So, to figure out how many centimeters per hour is equivalent to 10 meters per second, I'm going to give myself a little more room here. What I'm going to do is I'm going to convert that 10 meters per second. To do that, I need to do some multiplication. Now, if I multiply by some number, I'm going to change this value, unless the number that I multiply is 1. So I want to multiply by 1. Now you might think, well, if you multiply by 1, aren't you going to just get 10 meters per second back? Yes, but we're going to multiply by 1 in kind of a different way. So here, I know that 100 centimeters is the same thing as 1 meter. Well, that's got to mean that if I divide 100 centimeters by 1 meter, well, this whole thing has got to be equal to 1. 100 centimeters is exactly the same thing as 1 meter. So I can multiply by 1 and not change this value. It'll still be 10 meters per second. But when I do that, we can see is our units, our meter units, are going to cancel out. So now my units are going to be centimeters per second. Now, I can do the same thing here. I can do the same thing to get rid of seconds. Instead of multiplying by centimeters over meters, now I'm going to multiply by seconds over minutes. So I know there are 60 seconds in 1 minute. Similarly, I know that there are 60 minutes in 1 hour. And if I just look at my units here, I can see that the seconds are going to cancel out. Furthermore, my minutes are going to cancel out. So that the only units I am left with are centimeters per hour. That's how I do my conversion. What it boils down to is really you're just multiplying by 1, but you're doing that in such a way that you get the units to cancel out. A lot of times you can build up this long chain of calculations. This long chain of calculations is going to have lots of different units canceling out so that you're left with something fairly simple. Now, at the end, all I have to do is just write out the math for this. So I'm going to take 10 times 100 times 60 times 60. So let's see, 60 times 60 is 3,600 times another 1,000. That will give me 10 meters per second is the same as 3,600,000 centimeters per hour. That's a lot to write out. We want to do that in scientific notation. So we'd say 3.6 times 10 to the 1, 2, 3, 4, 5, 6 centimeters per hour. Suppose I'm giving you directions. I say, all right, to get to the outside scoop, you want to go 100 meters to the first stop sign, and then you want to go another 50 meters to get to the outside scoop. Okay? That's easy enough to do. Right? You can add those two distances together and figure out that in total, if the first direction is to go 100 meters, and then the next direction is to go another 50 meters, well, then the total is just going to be 150 meters. That's how far you're going to have to travel to get to the outside scoop. Now, I could have said that slightly differently. I could have said, all right, well, here's what you're going to do. You're going to go 300 feet to the stop sign, and then it's just another 50 meters after that. You could do that too, right? You could go 300 feet and then go another 50 meters. I'd have to do some converting to figure out what the answer to this is. I'd have to know that 300 feet was about the same as 100 meters. But you'd still get about 150 meters at the end. Okay. So here we're just adding two different distances that have different units. No problem there. However, if I were to say instead, first go 100 meters to the stop sign, and then go 50 kilograms, well, that's just stupid, right? It doesn't make any sense to go 50 kilograms, right? I can't travel 50 kilograms. I can lift up 50 kilograms. I can gain weight. I could put on 50 kilograms. But walking 50 kilograms, that doesn't make any sense. Meters and kilograms are categorically different units. And that's an important point behind what's known as dimensional analysis. So there's a difference between dimensions and units. And it's a subtle difference, but it's a very important one for what we're going to be doing throughout this course. So we need a good definition of dimensions and a good definition of units. Here's what we came up with last year as a class. We said that dimension, the dimensions of some physical quantity, really tell me what type of physical quantity it is. type of physical quantity. So for example, the type of physical quantity, it could be some type of length. Could be some type of time. Could be speed. Could be any number of things. Could be a wide variety of different types of physical quantities. However, if I'm going to add a length to something else, I've got to add it to another length. I can't add a length to a time. I could add a length to a length measured in different units, so I could add centimeters to meters, but I can't add centimeters to seconds. That doesn't make any sense. So that's what we mean by dimension. Units is just what I measure with. So the unit is the type of measuring stick you use. For example, we could measure things with a meter stick. Could be centimeters, miles, light years. We could measure time with the second hand of a stopwatch. We could measure it in minutes, hours, centuries. We could measure velocity in miles per hour. We could measure it in meters per second. We could measure it in a bunch of different ways. But for every physical quantity that we have, there's a bunch of different ways that we can measure it. The unit just tells me what type of measurement I'm making. What unit am I using to measure it? Well, I could use meters, seconds, a variety of other tools. However, I can only add things that have the same dimension. It's important to make your equations dimensionally consistent. What this means is that if I have meters on one side of an equation, I've got to have meters on the other side. I can't have seconds or meters per second. I've got to have the same units on each side of the equation, same dimensions on each side of the equation. So to see that, let's just look at, again, a very simple example. Here you are, you're running. And you're running some distance, which we'll call delta x. You're doing that for some time, delta t. Let's say you run for 3 seconds. And let's say you're running at a speed or a velocity of 2 meters per second. And I want to find what delta x is. Well, clearly I want to get units of meters because I know delta x is a distance and I measure distance in meters. So I want delta x, which again is in meters. And let's say I want to come up with an equation for that delta x. Well, looking at this, I know I have to make this dimensionally consistent. So I want to set that equal to velocity, maybe to some power, times delta t to some power. Well, I know velocity is measured in meters per second. I know delta t is measured in seconds. Now, for this example, it turns out that the powers are pretty simple. I just put them to the first power. So I don't need to take v squared or v cubed. Because if I take them to the first power, I get 1 meter over 1 second here, and I get 1 unit of seconds here. The seconds units cancel out, and I have meters on both sides. That's fairly simple. We can also use dimensional analysis to figure out whether or not an equation is correct, or at the very least, whether or not it's wrong. So here I have 4 equations. Suppose you're working in your lab group, and each of your lab members comes up with a different equation for the answer. How do you tell which one's right? Well, looking at these equations, I have a bunch of different physical quantities. In this case, I have my time, which is measured in seconds. I have my initial position, which is measured in meters. My final position, also measured in meters. And then I've got velocity, which is measured in meters per second. Looking over here, I need to make sure that my dimensions are consistent. They're not consistent. I know that there's no way the equation can be correct. So let's start off. As soon as I see an inconsistency, I can eliminate that equation. So starting off here, I know x is in meters. I know x initial is in meters. When I square it, I'm going to get meters squared. So I have meters has to equal something in meters squared plus something else. Well, I already know that can't work. Can't have meters equal to anything with meters squared, so that guy's out. Now let's look at this guy. I have x final. I know that's in meters. I've got x initial here. That's also in meters, so we're good so far. I have meters is something in meters plus something else. Let's see if this is still going to work. Let's see, velocity is in meters per second. When I square that and multiply by seconds, I'm going to get, well, one of my seconds are going to cancel out, but I'm going to still have meters squared. So that's not going to work out. That guy's out. Let's see what we got here. Let's see, well, x is in meters. I'll try a different color here, just to make that more visible. X is in meters. Let's see, what else do we have? X initial also in meters, good so far. Velocity meters per second. I'm still going to only get 1 meter on top. But now I have seconds squared here. That's going to be bad because I only have 1 unit of seconds in the denominator. If I get 2 units of seconds, these are going to give me units of meters times seconds. That's not going to work. Units of meters times seconds can't be added to units of meters. So this guy's out. So hopefully by process of elimination, this last equation is what's going to work. Let's see. Here we have units of meters equals units of meters. X initial is in meters, plus units of meters per second, times delta t, which has units of seconds. The seconds cancel out. I get units of meters equals something else in meters plus something else in meters. That is dimensionally consistent. That might be the equation that works. So this is a powerful tool. Just by looking at whether or not the dimensions of your equation work out, by doing dimensional analysis, we can determine whether or not our equation is definitely wrong or not. Suppose you're trying to figure out the equation for some physical quantity. Perhaps you're trying to find the kinetic energy on a test. Well, you don't necessarily remember what the equation is. You have a hard time remembering the equation. Well, that doesn't necessarily matter because you can at least figure out part of the equation using dimensional analysis. So here's how that works. Suppose you want to find the kinetic energy. Well, kinetic energy has units of kilograms meters squared over seconds squared. Now, kinetic energy happens to be the energy of motion. So let's say you suspect that the formula for kinetic energy depends on the mass, which we know has units of kilograms. And let's say you also suspect it depends on how fast an object is moving. We know that the speed or velocity is measured in meters per second. So we've got our mass, our velocity, we've got kinetic energy. Well, we want to ask, how can I combine those 3 quantities in a way that gives me an equation that has consistent dimensions? Well, to do that, I could say that my kinetic energy is going to be equal to mass to some power. Maybe it's to the first power, maybe it's squared, maybe it's to the 2/5 power. We don't know, but it's going to be mass to some power which I don't know. I'll call the power x. Times the velocity to some power. which I'll call y. Again, maybe the velocity is squared, maybe it's cubed. We're going to use dimensional analysis to figure out what those powers are. The one other thing is that there could be some constant that's left over. So I'm going to write my equation like this. C is some dimensionless constant. What I mean by dimensionless constant is it's just some number that doesn't actually have any units to it. If it doesn't have any units to it, it won't affect the units on this side or that side. So for example, it could be 2, or pi, or 3.974216. Just some number that doesn't have any dimensions associated with it. So let's see what we can figure out here. I know my kinetic energy has units of kilograms meters per second squared, meters squared per second squared. Well, that doesn't have any units, so I don't have to worry about that. You could write it as its units are 1. The mass does have units, that has units of kilograms. Velocity has units of meters per second. I'm going to put this in x and y. Well, when I say it has units, when I say that my dimensionless constant has units of 1, I can multiply 1 by anything and have it not affect the answer. So this doesn't even matter. I'm not even going to write that. There, we're going to have units of kilograms to the x power, meters per second to the y. Now if I stare at this for just a little bit, this doesn't have any kilograms in it. This has 1 kilogram in it. So to get kilograms on this side, I am going to need x is 1, so that I have mass to the first power. Over here, I've got meters over seconds. Here I have 2 units of meters over 2 units of seconds. So then I just need to square my velocity. My y has to be 2. If I want to write my equation out with those exponents, we can see that my kinetic energy is going to be given by some constant, I don't know the constant, times the mass to the first power, which I'm just going to write as m, times my velocity, but I know my velocity has to be to the second power, so it'll be to v squared. It turns out your actual kinetic energy formula is very close to this. The only difference is the kinetic energy, the unknown constant, the dimensionless constant, is 1/2. So if you were to do this on an exam, if you were to get that far, you get a good chunk of the credit for that problem. Because I know you're understanding the physics and how to do dimensional analysis, even if you couldn't remember the exact equation. Let's give you guys an example to play around with. We're going to do a non-trivial one here. Let's say you want to find the speed of sound. All right, well, let's write the speed of sound as Vs for velocity of sound. That's the speed of sound. That's going to be in meters per second. I want to come up with an equation for the velocity of sound. To do that, I need to know what the velocity of sound is going to depend on. What could it depend on? Well, it could depend on the air pressure. Maybe changing the air pressure increases or decreases the velocity of sound. So I'm going to just put big P here. That's the pressure. That's the pressure in the air. Now, air pressure, we've got to make sure we have the right units to get our dimensional analysis right. Air pressure is going to have units of kilograms over meters second squared. Okay, so that's one thing my velocity of sound might depend on. What else could it depend on? Well, maybe it depends on the density of the air. That looks like a P. It's actually the Greek letter rho. This is for air density. Air density, in fact any density, is going to have units of kilograms divided by meters cubed. Anything else that might affect speed of sound? I don't know. Maybe let's put maybe it's affected by the volume of the room that I happen to be in. So we'll call that volume. Volume gets units of meters cubed. The only other thing that it could potentially depend on is some dimensionless constant. I'll put that out in front as a C. Let's just remember that dimensional analysis cannot be used to figure out what a dimensionless constant is going to be. But usually, if we're just doing a ballpark estimate of what the velocity of sound is, that constant is going to be like a 2 or a 3. It's not going to be like a million. So we should be able to get a rough estimate of how big our sound is. Now what we want to do, what you're going to want to do, is see if you can figure out what exponents I put in here. So we'll say it's p to the x power, rho, the air density, to the y power, and then volume to the zth, how do I say that? Zth power. So see if you can use dimensional analysis. Again, we just want to combine pressure, air density, and volume in such a way that when I multiply these things together, I get units of meters per second, the units of the speed of sound. Because I'm pretty much guaranteed that since I need the dimensions to work out, this equation is going to be roughly correct. So see if you can figure out what these values are. Maybe it's pressure squared, maybe it's pressure to the 1/3, we don't know. But by combining these different units, you can figure it out. One of the most useful tools I can give you is teaching you how to read a physics equation. So it's said that a picture is worth 1,000 words. An equation is worth a lot more than that. So let's go back, as an example, let's go back to the kinetic energy equation that we derived using dimensional analysis. So we said kinetic energy is equal to, we looked this up, that was not from dimensional analysis, but it's equal to 1/2. And then dimensional analysis gave us that was mass to the first power times velocity squared. Now we want to remember that kinetic energy is the energy of motion. So even without having gone over energy yet, we can still do a pretty good job of figuring out whether or not this equation makes any sense. So I know it should depend on the mass of an object times the velocity squared. Let's see if that makes sense. Ultimately, the only question you want to ask is, does this make sense? All right, well, it's the energy of motion. Well, if I have something that's moving faster, so if I have a faster velocity, then presumably it took more energy to get that faster velocity. If something's moving faster, it should have more energy of motion. If I increase my velocity, even if I don't do anything to the mass, it should be true that the kinetic energy goes up. If I increase the V, keep the mass constant, kinetic energy is going to go up. That seems to make sense. The mass is a little bit trickier. It's the energy of motion, but why should mass have anything to do with motion? Well, let's think. Suppose, here's you. You toss a baseball at 10 meters per second. Tossing a baseball at 10 meters per second is not that hard. Pretend this is a baseball. There. 10 meters a second. That's not too hard. However, if this is you, and you're pushing a big truck, and you want the truck to go 10 meters a second, that's going to take a lot of effort. You're going to have to push for a very, very long time. So the bigger mass I have, the more my kinetic energy should go up. If it takes more energy to move a truck, it should be true that the truck has to have more energy. So if I do the same thing, keeping velocity constant, and still 10 meters a second, you make the mass increase, it should take more kinetic energy. If I make the mass bigger, keep the velocity constant, this equation says that the kinetic energy has to get bigger because I have to do the same thing on both sides to keep the equation equal on both sides. Works in reverse too. If I make the mass or velocity smaller, say I make the mass smaller, my kinetic energy has to go down. I've got to have less energy for smaller masses. This is what I mean by reading an equation. You should be able to look at an equation and see, if I increase the mass, what happens to the thing on the other side? What happens if I increase the velocity? What happens if I increase the velocity and decrease the mass? Well, that gets a little bit trickier. So if this goes up and this goes down, it's going to depend on how much one goes up and the other goes down. That's going to be a little bit trickier to figure out. To do that, we're going to have to do something called scaling. Figure out what happens if I change multiple ones of these quantities, multiple physical quantities in this equation. Now we're going to talk about something called scaling. So we're going to define scaling this way. Scaling is what happens to one quantity when you change another quantity. Now, a typical example of this is building scale models. So, for example, I have here a scale model, basically a matchbox version of the Batmobile. Batman! We're going to compare our actual Batmobile to the model Batmobile. So I went online to Wikipedia, looked up some stuff about the actual Batmobile, and here's some figures I came up with. It's about 226 inches long. It's about 4,500 pounds. Now here is my model Batmobile. It's about 3.75 inches long. We're going to try to see if we can calculate how much it weighs just based on a scaling relationship. So we are trying to convert from actual Batmobile to the model Batmobile, which means we're converting a few different things. I'm going to go from the actual length of the Batmobile to the model length. I'll call the actual length L, I'll call the model length L prime. On top of that, we know the actual length of the Batmobile is 226 inches. The actual length of the model was 3.75 inches. 3.75 is about 1/60th of 226 inches. So now I want to do the same thing with the weight. So I can say, all right, the weight of the actual Batmobile is 4,500 pounds. Okay, well, let's just do the same thing. Let's see what happens. 1/60th, let's take 1/60th of 4,500 pounds, and I get 75 pounds. 1/60th of 4,500 pounds is 75 pounds. This is my Batmobile. It is not 75 pounds. My model Batmobile is not 75 pounds. Where did I go wrong here? Well, the problem is the weight, call this the weight. The weight of an object does not scale proportionately to length. It is not that weight is proportional to the length of an object. This is not correct. How does weight scale with length? So if I make myself twice as tall, you would expect that I might weigh twice as much. And if the only thing I did was change my height by a factor of 2, I would weigh twice as much. However, I would also look very, very weird, because essentially you're stretching me out only in one direction. Really what you want to do is change not only my height, but also my width and my depth. So we want to change 3 length distances to get the equivalent change so that I keep all my proportions the same. So if I am trying to figure out how my weight scales, I can't look at just the length, I've got to look at the length times the width times the height. So we're going to do that now. So weight, if I look at my actual Batmobile, weight is going to be proportional to, not the length, but the volume of the Batmobile. Bigger volume means, assuming it stays at constant density, means it's going to have more weight. Well, volume is going to scale as the length cubed. I measure volume in units of liters, which I can convert to meters cubed or centimeters cubed. Since I have a distance cubed, I'm going to be measuring in terms of length cubed. Right, so that's my actual Batmobile. The model Batmobile is going to work the same way. The weight, which I'll call W prime because now we're looking at the model, the weight is going to be proportional to, or is going to scale as, this symbol. We call that scales as. The weight is going to scale as the volume. It's going to be, scales as just means it's proportional to, scales as the volume, which is going to scale as the length cubed. Well, I know my new length is 60 times smaller, my model length is 60 times smaller than my original length, which means my new weight is going to be 60 times smaller than the original length. So I can say that this is going to be proportional to the original length over 60. Again, it's just because my length, my new length is 60 times smaller than the original length. I'm just going to plug that in. That's going to be that cubed, which means this is L cubed over 60 cubed, which means my mass is not going to be 60 times smaller than it was originally. My model mass is not going to be 60 times less massive as the actual Batmobile. It's going to be 60 cubed times smaller. So that's why we've got 75 pounds. It's a much bigger number. Plugging in the cube root of 60 here, if I scale that down, this means my weight is going to be 60 cubed times smaller, which in this case gets you about 9.4 grams if you plug in the mass and do your conversions correctly. If we actually weigh our Batmobile, our model Batmobile, it turns out you get something around 10 grams. So this tells us that the scaling procedure we're using actually works. Again, the trick here is that not everything scales proportionately to other things. In this case, my weight scales proportionately to volume, but it doesn't scale proportionately to the length. It scales proportionately to the length cubed. Different things, different physical quantities change at different rates. In this case, the length doesn't change as fast as the volume does. If I change the length by a factor of 2, I'm going to change the volume by a factor of 2 cubed, which is actually going to be a factor of 8. Let's do an example here. It's commonly said that ants can support 50 times their own weight. That seems pretty impressive, but what does that even mean? More specifically, I want to know, what are the chances that giant ants are going to take over the Earth? All right, we're going to build a little table here, and for convenience, I'm going to work in kind of funny units, very peculiar units. I'm going to be working in units of ants. So we're going to start off with the length of one ant in this column. What's the area of an ant? Well, it's the area of one ant, so that's going to be 1. The volume of an ant is just the volume of one ant. Again, we're working in units of ants here. The ant weight is just the weight of one ant, and the weight that the ant can lift Well, that's supposed to be 50 times the ant's weight. So for one ant, one normal-sized ant, we've got its length is one length, its area is one area, its volume is one volume, its weight is one weight, and the weight it can lift is 50 times the weight of the ant. All right, let's see where we can go from here. Let's make the ant 10 times bigger. So an ant is about a millimeter tall, maybe 2 millimeters tall. Let's make it 2 centimeters tall, much taller ant. That means I'm making its length 10 times bigger. If I want to know the area of the ant, well, area scales as the length squared. Scales as the length squared. So that means its area is not going to be 1 unit. It's not going to be 10 units bigger. It's going to be 100 times bigger. Because the length got 10 times bigger. Area has 2 lengths in it, therefore I have to take the length times the length. It's going to be 100 times bigger. The volume is going to scale as the length of the ant cubed. Volume is measured in meters cubed. It's length times width times height. That's 3 distances. If all of those lengths get 10 times bigger, I'm going to get 10 times 10 times 10 times bigger. The volume is going to get 1,000 times bigger. My volume's 1,000 times bigger. What about my weight? Well, we just showed before that weight is proportional to volume. So the more volume I have, the more weight I'm going to have, assuming we're at constant density, assuming I don't get any more or less dense. So if it's proportional to the volume, and the volume is 1,000 times bigger, that means the ant is going to weigh 1,000 times more. 10 times longer, 10 times wider, 10 times taller. I'm going to weigh 1,000 times as much as I do right now. The weight the ant can lift is a bit more peculiar. How does that scale? Well, if you think about what it takes to lift an object, what it means is that your muscles are flexing. So it should be proportional to the strength of your muscles. Muscles are providing some tension. And for wider muscles, muscles that have a bigger cross-sectional area, you're going to be able to get more force. Basically, there's more muscle fibers that are doing the pushing or pulling for you. So if that's the important factor here, if the strength of the ant is going to be proportional to how much weight it can lift, and the strength is proportional to the cross-sectional area, then it should be true that the weight lifted is proportional to the area as well. So that's going to be proportional to the area as well. My area is 100 times bigger. Therefore, the weight I can lift is going to be 100 times bigger. So that's going to be 100 times 50. So it can support 5,000 pounds. An ant that's 10 times bigger, if it can support 50 times its own weight when it was normal sized, now it's going to be able to support, let's see, it's going to weigh 1,000 times, 1,000 times more than it did before. It can support 5,000 times more than it did before. But now, it can only support 5 times its own weight, because it's bigger. That's for an ant that's 10 times bigger, about 2 centimeters tall. Let's make it even bigger. Let's make it 100 times bigger. So now my ant is not 2 centimeters tall. It's now 20 centimeters tall. It's about 2/3 of a foot. It's about this big. Here's my ant. 100 times bigger. All right, well, how many times bigger is the area? Well, the area scales as L squared. So therefore, it's got to be 100 times 100 times bigger, because it's going to be 100 squared times bigger. 100 times 100 is how big? 10,000. 10,000, I'm going to do this in scientific notation. 10,000 is 10 to the 4th. Similarly, if I look at the volume, I want to know how many times bigger is my volume. If I make the ant 100 times bigger, well, now it's going to be it's going to scale as L cubed. Volume scales as L cubed. So we're going to have 100 times 100 times 100, L cubed times bigger. That's going to be how many times bigger? It'll be 1,000,000 times bigger. 1 million is 10 to the 6th. So now my 20 centimeter tall ant is 1,000,000 times has a million times as much volume, which means, since weight is proportional to volume, it's going to weigh a million times more. Still an ant. An ant was really tiny to begin with, so a million times more isn't hugely big, but it's still a million times bigger than the ant started off with. Well, what does that do to the weight that the ant can lift? Let's see. Here we are, we're scaling as the area. My area is 10,000 times bigger than it was before. Here we are, we could lift 50 times our own weight before. Now I've got to get 10,000 times bigger. So now, the ant can lift 5 times 10 to the 5, 500,000 times more than it could when it was just normal sized. So if I increase the ant by a factor of 100, now it's 100 times bigger, it's 20 centimeters tall, about 2/3 of a foot. Its area has gone up by 10,000, its volume and its weight have gone up by 1,000,000. The weight it can lift has gone up by 500,000. Or it's gone up by 10,000, but now it's 500,000 units. And we can see an interesting thing happens here. Now look here, that's 1,000,000. That's 500,000. Now it can't even lift itself. The weight it can support is actually smaller than the weight of its body. So it can't even pick itself up. And it's only going to get worse from here. Let's say I made a really big ant, a human-sized ant, an ant that was as tall as me. Well, that ant would have to be 1,000 times bigger than it is at present. 1,000 times bigger than a normal ant, which means its area is going to go up by 1,000 squared. 1,000 squared is 1,000,000, 10 to the 6. Its volume is going to go up by 1,000 cubed. 1,000 cubed is 10 to the 9. That's 1,000,000,000. It has 1,000,000,000 times more volume than it did originally. It also has 1,000,000,000 times as much weight. It's 1,000,000,000 times more heavy. What about the weight it can lift? Well, before, when it was just a normal, regular ant, it could lift 50 times its own weight. Now, I'm looking at how the area scales. It can lift 1,000,000 times more weight than it did originally, which means it's going to be able to lift 5 times 10 to the 7. So that's about 50 million. It can lift about 50 million of its original body weight, its original tiny body weight. But now it weighs 1,000,000,000 times more. 50 million, a lot smaller than 1,000,000,000. So this just gets worse and worse for our giant ant. So, take-home message, you can sleep well at night because you know giant ants are not going to be able to take over the earth. Now it turns out there is an easier way to see this rather than just doing out a giant table. I can look at the scaling relationships in graph form. So how can I visualize these relationships with a graph? Well, let's say I'm making a plot of L squared and a plot of L cubed. Remember that L squared tells me how much weight the ant can lift. L cubed tells me the body weight of the ant. Well, if you plug this into your calculator, you should see something like this. Right? I'll plot L squared in green. I'll plot the body weight of the ant in orange. Here we go. Here's L squared. This is proportional to the weight that the ant can lift. If I plot L cubed to represent the body weight of the ant, I'm going to get a graph that looks like this. Now initially, the L cubed graph will always start below the L squared graph. So I'm guaranteed that for small sizes, plotting this as a function of L, for small sizes, the weight that I can lift is going to be bigger than my actual weight. But as L gets bigger, the L cubed grows even faster than the L squared. So it's going to shoot off like this. And at a certain point, those two lines intersect each other. At this point, the ant can barely lift its own weight. If it gets any heavier, it can't pick itself up and bring itself around or walk or do anything. There's a certain crossover where one function takes over the other. So we can see graphically that at a certain point, just because of these scaling relationships, we know that an ant can't support its weight anymore. And it's not just ants. This is what limits humans to being certain sizes as well. This is why if you look at big, tall people, like people who play, people who are setters in NBA basketball, they tend to get bad knees and bad joints very quickly because they're supporting a lot more weight. Even though they have more area to support it with, that doesn't matter. It's the size scale that matters. At a certain point, human bodies just aren't stable because the weight you can lift is not going to keep up with your body weight.